Okay, so this is going to be one of those topics that let me restart this. We are going to talk about the cross and dot product. And the cross and dot product is a topic that you usually pick up in math courses. Most of the time in college physics courses, they expect that you know how to do this. And in high school physics courses, they skip over it. So this is not one of those topics that's on AP, but I definitely incorporate this in here because if you are going to take any upper level physics courses, basically when you leave here and you're taking a calculus-based course, especially in a second semester, you're going to need to know a little bit about the cross and dot product because we run into the concept. With the advent of graphing calculators and computer systems, a lot of the mathematical skills, the hands-on skills that I'm about to show you have been pushed off for other concepts. In fact, we used to teach the cross and dot product in our advanced math concepts courses, and we spent some time on matrices, augmented matrices, Cramer's rule, things like that. And I don't think you spend very much time, if any, on those subjects anymore. Again, because we now have calculator systems that have not made the math obsolete, but have made it very easy to do without the time requirements. Now, if you were going into a more advanced math program, you take courses like linear algebra and some of the other advanced courses in mathematics, 200 and 300 level math courses, and study some of these concepts to some more depth. We, again, are going to use the cross and dot products. We have actually already used the dot product, and we'll use the cross product in the near future tomorrow when we talk about torque. But for right now, I want to focus in on the mathematics of what the cross and dot product are. We can talk about what their meanings are and things of that nature, but just being able to do the plug and chug math, we need to be able to do that first. And so here's how this is going to go. Again, we are going to talk about the cross product and the dot product. Now, these are both multiplication processes of vectors. So there's a third one, which is called scalar multiplication, and we have actually been doing scalar multiplication all year. And so when we take a vector such as 30 newtons and we want to scale it to draw it, we multiply by a fraction. Remember, you'll hear me say there is no such thing as division. Division is just multiplying by the inverse, so or multiplying by a fraction. And so if I want to scale this, maybe I want to scale this so I can draw it, and I can do 30 newtons times 1/6, and I go that's 5 centimeters, and I'm able to scale it. So a scalar just takes a vector and it makes it larger or smaller without changing anything with its angle. So if the angle was 30 degrees, the answer is going to have a 30-degree angle to it. We just scale the magnitudes. So that's just scalar multiplication. What we're going to talk about is taking a vector times a vector. The 1/6 was not a vector. The 1/6 was a scalar number. So what we're going to do here is we're going to take two vectors and multiply them together, and we get two different possible solutions. We get the cross product. This gives us a vector. This is a vector product. Product means what we get when we multiply numbers together. We've already done vector addition and vector subtraction. Again, subtraction is just adding the negative, but we've done that. We know how to do that. We know how to do the scalar multiplication. This is going to be a vector times a vector. This is something we haven't really done officially until this point. So we take the cross product, we multiply a vector times a vector, and we end up with a vector answer. And then there's the dot product, where we take a vector times a vector and we get a scalar answer. And depending on the mathematical operation and what it is that we're multiplying, we could either use the cross or the dot. What's interesting is with the cross product, we generally use the X symbol to represent that vector multiplication, 30 newtons at 30 degrees times 50 newtons at 50 degrees, and we put the X in the middle, and that's why we call it the cross product. And the vector product, we put the little dot. So I mean, we call them what sign goes between them. But we should recognize that the cross product is a vector times a vector, giving us a vector, and the dot product is a vector times a vector, giving us a scalar. Where does this come into play, you might ask? Well, we'll talk about this a little bit more, but work is a scalar. Work is a scalar concept, and it comes from doing the dot product. And torque is a vector concept, and it comes from doing the cross product. And the interesting part is that the equations look very similar to each other. The work equation is force dot displacement, and the torque problem is force cross displacement. Very similar. There's fundamentally a different solution and they have a different value. If force is 30 and displacement is 50, and their angles are 30 and 50 respectively, the force times the displacement in work and the force times displacement in torque will give us different mathematical answers. They will also have different meanings of those answers. So we are going to see these concepts. Let's look at the math. Let's just say I give you two vectors. So the vectors I'm going to give you today would be 30 newtons at 20 degrees and 50 newtons at, let's make it 60 degrees. And we want to do first the dot product on it. So when we're talking about the dot product, we can do dot product from polar coordinates, or we can do dot product from the Cartesian coordinates. You get to do it in the method that you are in. So if you're in Cartesian, do it in Cartesian. If you're in polar coordinates, do it in polar coordinates. So you need to know both methods. If you're a hybrid, you have some in each of the types, you're going to have to put all of your numbers into either polar or Cartesian. But here's how you do it with polar. With the polar coordinates, we are going to take, we'll call this vector A, and we'll call this vector B. And so we're going to take vector A dot vector B, and we're going to do this in polar coordinates. And so what you would do is you would take the magnitude of A, multiply by the magnitude of B, and then you multiply by the cosine of the angle between the two vectors. It's not the angle of the vectors, it's the angle between them. So what is the angle in here? And so that angle in this case is 40 degrees. 20 degrees to 60 degrees, that's a 40 degree angle. There you go, a 40 degree angle. And so we would put in here the cosine of 40. And we will get an answer. We'll get the correct answer, 30 times 50 times the cosine of 40. Very simple process. We have seen this. You know that when we did work, we did force times displacement times the cosine of the angle. And I just told you that work's a dot product. And so you could see a little bit more of why that's the case. And so I get 11,049, and we could put down the units here. This would, in this case, I'm not sure what a Newton times a Newton is. It's a Newton squared, I guess. It's its own unit, but that's irrelevant to the problem. What I care about right now is the magnitude. And then we get 30 times 50 cosine 40. It's 1,149. Now that's a very simple way of doing it, but sometimes we have it in the Cartesian coordinate system. I'm just going to convert here very quickly. So we have 30 at 20 degrees. We have 50 at 60 degrees. We need to break these into their components. So this is our I hat component and our J hat component. So I do 30 cosine 20. And when I do that, I end up with 28.1, 28.2. And I do 30 sine 20, and I get 10.3. Now, we will get a more precise answer if we take this out a few extra decimal spots. I might show you that here in a minute. And then we can do the same with 50 cosine 60, which is going to be 25, and 50 sine 60, which is going to be 43.3. So when I multiply, so what I've done is I've made my basic vector table, and we are going to do vector multiplication, not vector addition. So I don't just add the columns, I multiply the columns. So I'm going to take 28.2 times 25, and I get 705. And then I'm going to take 10.3 times 43.3, and I'm going to get 445.99. So really 446 would be the answer. Now, as I told you, rounding makes a difference here. So 446 is the value. And so what we do is we're going to add these together. Add these two numbers together. 705 plus 446. And when I do that, I end up with 1,151. That's very close to 1,149. In fact, as I said, if I take this out to some additional decimal spots, I will actually get that. One of the places I noticed right away when I was doing this was that 30 sine 20 was 10.26. So if I had just taken this out to one more decimal spot, I would have 10.26 times 43.3, and I end up with a value now of 444. 705 plus 444, 1149. I get the exact same answer. So it's just a rounding thing, but that is how you do the dot product. You take the x components and you multiply them together. You take the y components, you multiply them together, you add them together, you get the same exact answer as you got from doing 30 times 50 times the cosine of 40. Mathematically, it is the exact same thing. So two ways of doing the dot product are there. The next topic is the cross product. And before we go to the cross product, I'm going to stop for a moment and let you think about that. Okay, so now we're going to move on to the cross product. And when we take a look at the cross product, what we are going to see, what we're going to see is that we're going to use the same exact vectors. I just want to make sure that I have them correct. 50 at 60 and 30 at 20. Okay. So 50 at 60 degrees and 30 at 20 degrees. And again, this is going to be the cross product. And so what we would say, remember this was vector A over here, and this was vector B. What we'd say is A cross B. Vector A cross B. And to do this in polar coordinates, you may have already guessed what you're going to do, but you're going to say 30 times 50, 30 cross 50, sine of the angle between them, which is 40 degrees. And so 30 times 50 times the sine of 40 gives us 964. Okay, so that's going to be the cross product value. This is a vector. So this would have both a magnitude and a direction. The math you just did will not explain the direction. I'll explain to you how you get the direction at the end of this, but note that this should have with it, when you do the cross product, you should have a direction there, north, south, east, west, in, out of the paper. So what we're going to do now is look at this from the perspective of how you do the cross product in Cartesian coordinates. And this gets interesting. So again, we're going to set up the same thing we did. 30 at 20, 50 at 60. I'm going to set up a vector table. This is going to be a little bit different than the ones we're used to. I'll explain why in a moment. First off, we are going to have an I hat, a J hat, and a K hat. What's the K hat values? We'll get to that in a moment as well. So 30 cosine, we're going to fill this out exactly the same way we did previously. So we have 28.2 and 10.26. And then for the Y values, we'll have 25 and 43.3. This does not go in the K direction. So we put this in as zeros. These vectors are laying on the plane. Now, if they're coming out off the paper, you would put some values here. And this is one of the reasons that you need to know how to do this, is because when we're dealing with vectors that are going in 3 dimensions, which the real world does sometimes have 3 dimensions in it, you need to understand how to mathematically manipulate the vectors. And so what we will do now is we're going to go fishing. You're going, what do you mean he's going fishing? Well, earlier in the year, I explained to you the idea of a nug and a gun. Okay, for those of you that missed this, I said that in school we don't talk about guns very often. So if this was a gun, okay, then this was the stock back here. Then, and I'm not an artist, okay, then this was the nug, right? Gun and nug, right? So you have your gun and nug. Now, with that same logic in mind, this is the letter alpha. This is the letter alpha. We've seen this. We've used this, right? Alpha. And this is a fish. Okay? Keep that in mind. We're using fish, not alpha. It's important that we get this in the correct direction. If we don't, we'll mess up. So this is just a device, a mnemonic device type thing that we will use to help us do our math. And so to do cross product multiplication on vectors, we are going to multiply the components together and come up with a vector answer. And that vector answer will have an I component, a J component, and a K component. So when we're dealing with the calculation of the I component, the first thing we're going to do is cross off the I component. So when we're solving for I, we cross off I, and then we do our mathematics by going fishing. So what we'll do is we will take the first direction, which is down this way, and we'll multiply them together. And then we'll take our second direction, which is down this way, and we will multiply them together, and we'll subtract the second from the first. So it'll look something like this. it would be, in this case, it would be 10.26 times 0 minus 0 times 43.3. And when we do that, we end up with 0 I hat. It's a number. We then do the same thing for the j value. We cross off the j. I crossed it off. You do this mentally in your mind. What I usually say is you put your finger over j, and then we go fishing. And to go fishing, we're going to go like this again. And we're going to multiply and then subtract the product of the second one. Product right, product left, if you want to think about it that way. So we'll do 28.2 times 0 minus 0 times 25, and that will give us a value of 0 j hat. And then we do it finally for the k value. We cross off the k. There we go. We've crossed off k. And we go fishing again. And this time we're actually going to get some numbers that are not 0. And we will get 25. Oop, did that wrong. We'll get 28.2 times 43.3 minus 10.26 times 25. So you got to get your calculator out and do that. 28.2 times 43.3 minus 10.26 times 25, and you end up with the value of 964.6. Look at that. Again, a little bit of rounding here. If we take everything out to an extra decimal, I bet you we get exactly the same value. And so the cross product will give us the ability to solve if we can get the same exact value. What does this all mean? Well, before we get even to that point, I'd like to tell you about one extremely, if you didn't get to the point, it's extremely important thing you need to do at this junction in time. And that is, whatever the sign is of j, you change it. If j is positive, you make it negative. If it's negative, you make it positive. You must do that. Because what this could be written at, if we had the values after doing the math of 10 I hat, 20 j hat, 964 k hat, we would put a negative sign in there and switch it. And so mathematically, we could write this whole equation as 10 I hat minus 20 j hat plus 964 k hat. 964 k hat, right? You get that value. So this is just an example. The real example is on the bottom of the page. 0 doesn't really have a sign, so it's not a big deal here. The answer is just going to be 964.6 k hat. Back when we were in the early stages of learning physics, I swore everyone in to the physics gang and I taught you the right hand rule. Made you hold up your right hand and swear into the physics gang. Well, when we did that, we said that if this is positive x to the right and this is positive y up top, then you took your right hand and you put your index finger down the x, you took your middle finger and stuck it in the y direction. Your thumb would protrude out of the board, out of the screen like this in the y direction. Well, following that same logic, 964k is pointed not in the direction of x, not in the direction of y. That should have been that should have been the z value. Sorry, that would have been z. I don't know why I wrote y there again. That would have been your z value. Not in the direction of x, not in the direction of y, but in the direction of z, right? Your k values pointed out of the paper. Now, how do you get that? I told you back here on the left side of the paper, I said, hey, don't forget at the end, I have to tell you, you got to put a direction on that. Well, you take your right hand and you put your index finger in the direction of the 20-degree angle, index. You take your middle finger with your hand. So your hand will either be up or down. It'll be, the palm will be pointed up or the palm will be pointed down. The only way you can do this is your palm pointed up for this problem. You would put your index finger in the direction of y, and then your thumb would be coming straight out of the paper, exactly the same way. So this would be out of the paper, out of the board, out of the screen. And so that is how you do the cross product. So we have the dot product and the cross product. Their meanings we'll study some more, but mathematically, I want to make sure that you're able to calculate these values and understand that the dot product is giving you a scalar answer, and the cross product is going to give you a vector answer. Does anybody have any questions for me at this